Okay, so this week we will go to chapter 2. We will cover in this chapter section 2.1, graphs and tables for categorical data, and section 2.2, graphs and tables for quantitative data. So categorical data, you remember it is the same as to say qualitative data. So first, let's talk about graphs and tables for categorical data. The objective of this section is that you will be able to construct and interpret a frequency distribution and a relative frequency distribution for qualitative data. Construct and interpret bar graphs and construct and interpret pie charts. So, what are frequency distribution? This is a popular method used to summarize the values in a data set. The frequency or count of a category refers to the number of observations in each category. A frequency distribution for qualitative variable is a listing of all the values, for example, categories, that the variable contains together with the frequency for each value. Take example 1. What carriers do teenagers admire? So we list here 20 carriers: doctor, scientist, military officer, athletes, and we ask 20 students to answer which carrier they admire, they would want to follow. And here are the answer. The first student want to be a doctor. The second student want to be a scientist. The third doctor want to be a military officer. The fourth student also want to be a military officer. The fifth student want to be a doctor, and so on. So, count how many students prefer that particular career and summarize the data. So, we make this a table 2.2 into 2 columns. The first column, the variable, is a career that are doctors, scientists, military officer, lawyer, and athletes. So totally 5 different careers. And the frequency, if you look at the career doctor, student number 1, number 5, number 9, number 11, number 17, number 19. So totally 6 students want to be doctor. So we put in the frequency column number 6. Similarly, scientist has 5 students. Military officer 5 students. Lawyer has 3 students. And athlete has only 1 student in the survey. So the relative frequency of a particular category of a qualitative variable is its frequency divided by the sample size. A relative frequency distribution for a qualitative variable is a listing of all values that the variable contains together with the relative frequency for each value. So, let's take an example. What are the relative frequency of career preferences using the information in table 2.2? Here's a table 2.2. So we have 20 students participated in the survey. So the sample size is 20. There are 6 students who want to be doctor. So the relative frequency of the career doctor is 6 over 20. That means 0.3. Similarly, for scientists, this is 5 over 20. That means 0.25. Military officer, 5 over 20 also, so 0.25. Lawyer, this is 3 over 20. It's 0.15. and Atlas 1/20, this is 0.05. So totally, the relative frequency, this is, if you add all of them together, you get 1.00. So this is what is the relative frequency. Now we talk about bar graphs. A bar graph, it is a graphical equivalent of a frequency distribution or a relative frequency distribution. How to construct a bar graph? So on the horizontal axis, we provide a label for each category. And we draw rectangle that called bars of equal width for each category. The height of each rectangle represents the frequency or relative frequency for that category. And we ensure that the bars are not touching each other. Now, as example, let's consider bar graph of carrier preferences. We construct a frequency bar graph and relative frequency bar graph for the carrier preference distribution in table 2.2 and 2.3. So we have two bar graph A and B. So in the graph A, so on the horizontal axis, we put the carrier, doctor, scientist, military officer, lawyer, and athletes. And on the vertical axis, we put the frequency 1, 2, 3, 4, 5, 6. And because the carrier doctor has frequency 6, so the bar has a high 6. Scientist has frequency 5, so the bar has the high 5. On the graph B, relative frequency, instead of frequency, the vertical axis will be relative frequency that we put as 0.05, 0.10, 0.15, and because the relative frequency for doctor is 0.3, for scientist 0.25, for lawyer 0.15, and for athlete 0.05. So we have this the graph B, and if you can see that the bar here do not touch each other. So pie chart. This is graphical device for displaying the relative frequencies of a categorical variable. We take a circle and we divide into sections, that is slices or wedges, each section representing a particular category. The size of the section is proportional to the relative frequency. Let's take an example. What is a pie chart? For the carrier data from example 2.2. So the relative frequency are in the column number 2. We multiply the relative frequency by the 360 degrees. We get the degree for that section. For the section doctor, this is 0.3 times 360. So this is 108 degrees. For scientist, this is 0.25 times 360 degrees. So this is 90 degrees. And so on. So the total degrees for all the section must be 360 degrees. And we have, this is a pie chart for the carrier data, where the slice for doctor has 108 degrees. For scientists, this is 90 degrees. For military, 90 degrees. For lawyers, 54 degrees. And for athletes, this is 80 degrees. So in summary, frequency distribution and relative frequency distribution list on the values that are qualitative variable can take along with the frequencies or the counts or relative frequencies for each value. A bar graph is the graphical equivalent of a frequency distribution or a relative frequency distribution. And a pie chart are a common graphical device for displaying the relative frequencies of a categorical variable. A pie chart is a circle divided into sections, with each section representing a particular category. The size of the section is proportional to the relative frequency of the category. Okay, now we go to section 2.2, graphs and tables for quantitative data. The objective is that by the end of this section, you will be able to construct and interpret a frequency distribution and a relative frequency distribution for quantitative data. You can use histograms and frequency polygons to summarize quantitative data. You can construct and interpret stem and leaf display and dot plots. You can recognize distribution shape, symmetry, and skewness. Okay, as example 2.7. The National Center for Missing and Exploited Children gives an online searchable data based on missing children nationwide. The table 2.13 contains a listing of the 50 children who have gone missing from California and who would have been between 1 and 9 years of age as of March 4, 2007. Suppose we are interested in analyzing the ages of these missing children. Use the data to construct a frequency distribution and a relative frequency distribution of the variable age. So, first we have to construct the frequency distribution for the variable age, and we construct a relative frequency distribution by dividing the frequency by the total number of observations, or the sample size, that is 50. So if we use the example that are given on the page 54 is the table 2.13 of that we have that the number of missing children in age 1 has frequency 3, of age 2 has frequency 3, age 3 has frequency 2, age 4 has frequency 8, age 5 has frequency 9, age 6 has frequency 10, age 7 has frequency 6, age 8 has frequency 6, and age 9 has frequency 3. So totally 50 missing children. So the relative frequency, we take 3 divided by 50, we get 0.06. 2 divided by 60, we get 2 divided by 50, we get 0.04. 8 divided by 50, we get 0.16, and so on. So the relative frequency for the children, it is our column number 4. So the total frequency must be 1.0. So to have a more concise distribution, we must combine several ages together into classes. The classes represent a range of data values that are used to group the element in a data set. For example, consider example 2.8. 5 frequency and relative frequency distribution using classes. We combine the age data from example 2.7 into 3 classes and construct frequency and relative frequency distribution. So let us define the following classes for the age data: 1 to 3 years old, 4 to 6 years old, and 7 to 9 years old. For each class, we group together all the ages in that class. So now we have now 3 columns: class, frequency, relative frequency. Class, we have class 1 to 3, that means the children from the age from 1 to 3. Class 4 to 6, the children with the age from 4 to 6, and class 7 to 9, children with ages 7 to 9. So what are the frequency? So we have 3 kids in age 1, 3 in age 2, and 2 in age 3. So in this group, from 1 to 3, we have 3 plus 3 plus 2, so 8 children. Similarly, for the group from 4 to 6, we have 27. And for group from 7 to 9, we have 15. So the relative frequency, if one way that you can do that, you add the frequency of kids in the age group age 1, age 2, age 3 together, you get 0.16, or the other way, you could take 8 divided by 50, you also get 0.16. For the class from 4 to 6, you get the relative frequency of 4, 5, and 6, you get 0.54, or you take 27 divided by 50, you also get 0.54. And the same for class 7 to 9, the relative frequency is 0.3. So the total relative frequency is again always must be 1. Now, how to construct frequency distribution and histograms? We give here first few definitions. The lower class limit of a class equals the smallest value within that class. The upper class limit of a class equals the largest value within that class. The class width equals the difference between the lower class limit of 2 successive classes. So the class width equals the differences between the lower class limit of 2 successive classes. It is not the difference between the upper class limit and lower class limit. So it is something that student may make mistake. So using classes to construct a frequency distribution. Determine how many classes you will use. So determine the class width. So it is recommended, although it is not required, that you use the same width for all classes. Determine the upper and lower class limit, and you make sure that the classes are non-overlapping. So example, constructing a frequency distribution, the management amplitude test. Okay, let's come back to the lower class limit, upper class limit, and class width. So for this example, for the class 1 to 3, the low class limit, it is 1. The upper class limit, it is 3. For the class 4 to 6, the low class limit is 4. The upper class limit is 6. For the class 7 to 9, the low class limit is 7 and the upper class limit is 9. And now what is the class width? So class width here, if we have the class 1 to 3, and 4 to 6, so the low class limit for class 1 to 3, this is 1, and the low class limit for 4 to 6 is 4. So class width will be 4 minus 1 is 3. So for the class 4 to 6, the low class limit is 4, and for the class 7 to 9, the low class limit is 7. So the class width here is 7 minus 4 is also 3. So here both class widths are 3, so they are equal. Okay, example. Constructing a frequency distribution, the management aptitude test. So 20 management students in preparation for graduation took a course to prepare them to a management aptitude test. A simulated test provided the following score: 77, 89, 84, 83, 80, 80, 83, 82, 85, 92, 87, 88, 87, 86, 99, 93, 79, 83, 81, and 78. Construct a frequency distribution of this management aptitude test score. So, as the first step, we choose the number of classes. Usually, we use between 5 to 20 classes. We don't try to make more than 20 classes. As the number of classes increase with the sample size. So the more sample size, the more you may need to use classes. So for our example, a small group of students, a small data set will do just fine with 5 classes. So in general, choose the number of classes to be large enough to show the variability in the data set, but not so large that many classes are nearly empty. So the step 1, it is choose the number of classes. The step 2, it is determine the class width. For that, first we find the range of the data and divide this range by the number of classes you choose in step 1. This gives an estimate of the class width. Here, in our data, the largest, this is 50, is 99. And the smallest is 77. 77 is the smallest, and the largest data value is 99. Therefore, our range of data is 99 minus 77. That means 22. So in step 1, we choose 5 classes so that our estimated class width is 22 divided by 5. The range 22 divided by 5 classes. So the estimated class width is 4.4. But usually we use a convenient class width is an integer. So instead of 4.4, we take the class width 5. So take an integer, the closest integer, more than 4.4, not less than 4.4. Don't take 4, but take 5. So in step 3, determine the upper and lower class limit. We choose limits so that each data point belongs to only one class. The classes should not overlap. For example, you could define classes starting because the width of a class is 5 and we have a 5 class. So the interval become now 5 times 5, it is 25. That means that the interval now starting from 75 to 100 instead of from 77 to 99. We have from 75 to 100. So we divide the limit point we can take as 80, 85, 90, 95. And we have classes from 75 to 79, 80 to 84, 85 to 89, 90 to 94, 95 to 100. Avoid to take classes, say, from 75 to 80, 80 to 85, 85 to 90, 90 to 95, and 95 to 100 because we have overlaps at the limit. We have overlap at 80, 85, 90, 95. So the classes should not be overlapped, which is the reason that why we choose like that. So here the low class limit of the first class is 75. This is slightly below that of the smallest value in the data set 77. And the class width equal 5. Now we count how many students get the score in the class 75 to 79. We have 75 to 79. We have students with score 77, 79, 78. So 3 students. So we put here the frequency is 3 and 3 students is the total number of 20 students has a relative frequency 0.50. You take 3 divided by 20. So similarly, is a class from 80 to 84. You have 8 students. 8 divided by 20, you get 0.40 relative frequency. For the class from 85 to 89, you have 6 students. So the relative frequency will be 6 divided by 20, that means 0.30. For the class 90 to 94, we have 2 students. So the frequency is 2 and the relative frequency is 2 divided by 20. It means 0.10. And for the class 90 to 100, you have only 1 student. So the relative frequency is 1 divided by 20, so 0.05. So totally, you have frequency 20 and relative frequency 1. So histogram, it is graphical summary for quantitative data. We construct histogram using rectangle for each class of data. The height of the rectangle represents the frequencies or relative frequencies of the class. The width of the rectangle represents the class width of the corresponding frequency distribution. It is different from bar graph. And the low class limits are placed on the horizontal axis, along with the upper class limit on the rightmost class, so that the rectangles are touching each other. So example, histogram of management aptitude test score. Now we construct a histogram of the frequency of the management aptitude test score from example 2.10. So this is from this table. We construct now histogram. So find the class limit. The first step, we find the class limit and draw the horizontal axis. So the low class limit as 55, as 75, 80, 85, 90, and 95. The upper class limit of the rightmost class is 100. Now we draw the horizontal axis with the number 55, 80, 85, 90, 95, and 100 equally spaced. In step 2, we determine the frequencies and draw the vertical axis. We use the frequencies given in table 2.16. It is this table. The frequency, it is a column 3. So this frequency will indicate the height of the 5 rectangles along the vertical axis. So the largest frequency in this case is 8 and provides a little bit of extra vertical space above the tallest rectangle. So make 9 as your highest label along the vertical axis and provide equally spaced label along the vertical axis between 0 and 9. So in step 3, we draw the rectangle. We draw first rectangle. Its width is from 75 to 80 and the height is 3. This is the first frequency. And we draw the remaining rectangle similarly. So the resulting frequency histogram is shown in figure 2.11a. So from 75 to 80, it has a height 3. From 80 to 85, it has a height 8. From 85 to 90, it has a height 6. 90 to 95 has a height 2. And 95 to 100 has a height 1. The relative frequency histogram is shown in figure 2.11b. So now the height, it is for the first rectangle, the height is 0.15. For the second rectangle, the height is 0.4. For the third rectangle, the height is 0.3. For the fourth rectangle, the height is 0.1. And for the last rectangle, the height is 0.05. This is due to the the last column in this table, 2.16, 0.15, 0.4, 0.3, 0.1 is 0.05. So if you compare histogram and bar graphs, what you can see is that the bar graph do not touch each other. But it is not the case with the histogram. If you compare these two histograms, one using frequency and the other using relative frequency, you can see that they have identical shape. They are different only is the labeling along the vertical axis. Sometimes on the horizontal axis, instead of using the lower limit and upper limit, you could use the midpoint. Say for the class 75 to 80, the midpoint is 77.5. For the class between 80 to 85, the midpoint is 82.5. For class from 85 to 90, the midpoint is 87.5. For class from 90 to 95, the midpoint is 92.5. And for the last class, from 95 to 100, the midpoint is 97.5. So we could label the horizontal using the midpoint rather than the class limit. So frequency polygons. We provide the same information as histograms in different formats. We construct frequency polygon as follows. So for each class, plot a point at the class midpoint at the height equal to the frequency for that class. Then we join each consecutive pairs of points with a line segment. Now, example 211. Construct a frequency polygon for the management aptitude test data in example 2.10. So on the horizontal axis, we place the midpoint of classes 77.5, 82.5, 87.5, 92.5, and 97.5. Now, for the point 77.5, we plot a point with the height 3, because the frequency for that class is 3. For the point 82.5, we plot the point at the height 8. For class with the midpoint 87.5, we plot the point at the height 6. And for the other two classes, we plot the point at the height 2 and 1. And after that, we connecting the two consecutive points. So we have this polygon that go up from the point 77.5 to 82.5, go down to the point 87.5, go down to the point 92.5, and go down further to 97.5. Now, we will go to another kind of display of data, stamp and leaf display. Construct a stamp and leaf display for the final exam scores of 22 psychology students given below: 75, 81, 82, 70, 60, 59, 94, 77, 68, 98, 86, 68, 85, 72, 70, 91, 78, 86, 51, and 67 as a score of 20 psychology students under survey. First, we find the leading digit of the numbers. So each number has one of the following as its leading digit: 5, 6, 7, 8, 9. So number 75, the leading digit is 7. Number 81, leading digit is 8. Number 82, leading digit is 8. 70, leading digit is 7. 60, the leading digit is 6. So we see here we have 5 leading digits. We list them in increasing order. So 5, 6, 7, 8, 9. So we place these 5 numbers. We call them the stems in a column. 5, 6, 7, 8, 9. Now, after consider the tens, now we consider the ones placed for each data value. The first score 75 has stem 7 and has 5 in the ones place. We place this number called the leaf next to its stems. So we put 5 next to 7. Next, we find leaf for each remaining number and place next to stem. So, with the stem 5, that we have 2 score 59 and 51. So it has 2 leaves, 9 and 1. So we list both of them next to 5, but we put them in increasing order. So this is 1 and 9. For the stem 6, we have 60, 68, 68, 67. So 4 students with the score is with the stem 6. So we put the leaf next to the stem 6. They are 0, 7, 8, 8. We put in the increasing order. So for stem 7, we have 6 leaves, 0, 0, 2, 5, 7, 8. For stem 8, we have 5 leaves, 1, 2, 5, 6, 6. For stem 9, we have 3 leaves, 1, 4, 8. So this is stem and leaf display. It contains all the information that a histogram turn on. So another way of display data are dot plots. This is a simple but effective graphical display. Each data point is represented by a dot above the number lines. It is useful for comparing two variables. And each dot may represent more than one data point for large sample size. So, here is the dot plot of the managerial aptitude test score. The 2 dots above 87 indicates that 2 tests had the same score of 87. So from here you can see that Which test score was the most common? You can see that it is 83. The score 83 has three students. Okay, now we go to talk about the shape of the graphs, distribution shape, symmetry, and skewness. The distribution of a variable, it is a table, a graph, or a formula that identifies the variable values and frequencies for all elements in the data set. The shape of a distribution is the overall form of a graphical summary. The shape is symmetric if there is a line, that we call it axis of symmetry, that splits the image into halves so that one side is the mirror image of the others. So, if we come back to the distribution of the grade, using the histogram, then you can connect the bar to have a band-shaped curve. So this is an example of the band-shaped curves that it has a symmetry. So due to randomness of variable, data from the real world rarely exhibits perfect symmetry. So the chi-square distribution, which is not symmetric but is skewed, like in the example 2.14 or 2.15. So this is a so-called left skew, and this is the right skew. So, in summary, quantitative variable can be summarized using frequency and relative frequency distribution. Histograms are a graphical display of a frequency or a relative frequency distribution with class intervals on the horizontal axis and the frequency or relative frequency on the vertical axis. A frequency polygon is constructed as follows. For each class, plot a point as a class midpoint at a height equal to the frequency for that class, then join each consecutive pair of points with a line segment. Stem and leaf displays contain more information than either a frequency distribution or a histogram, since they retain the original data values in the display. In a dot plot, each data point is represented by a dot above the number line. An image has symmetry or is symmetric if there is a line that is called axis of symmetry that splits the image in half so that one side is the mirror image of the other. Non-symmetric distribution with a long right-hand tail are called right skew, while those with a long left-hand tail are called left skew. Okay, so this is the content of the section 2.1 and 2.2.